Yeah, Assalamualaikum and good afternoon. So today we start our lecture from chapter 1, but actually from Porter textbook, it is in chapter 4. So the title is The Differential Form of the Fundamental Laws. So before we go further to analyze by using this idea, I would like to share with you about the coordinate system. So here, as stated here, so we have two coordinate system. One is Cartesian coordinate and the other one is polar coordinate. So for the Cartesian coordinate, I think we already familiar with this coordinate. It is about the x and y. And polar coordinate is actually a coordinate that illustrate motion in circular shape, in circular motion. Okay, so this is the explanation of the coordinate system. You may read from this slide. So the idea of Cartesian coordinate is we have at least dimension, which is x-axis and y-axis, and then we describe the location of that certain particular particle by express the location of x and y. So I think you are familiar with this. For example, we have one location here. So we express the location at this point as 2, 3. So 2, 3 here means in x direction, so there are 2 units, and in y direction there are 3 units. Okay, so and then if we want to evaluate this by using three-dimensional, so we will have a z-axis here. So z-axis will become normal to the screen. So means that this is the x, so this is the y, and this will become the z-axis. So for location in in three-dimensional, you may write as x, y, and z. So if the coordinate is 2, 3, and 5, for example, so the 5 here means it is 5 unit on y-axis. So and then as you know, in fluid mechanics 1, we always describe fluid mechanics in terms of pressure and velocity. So to describe the velocity in two-dimensional axis for x and y axis here, so we could say that if one molecule move from here to here, okay, so the velocity actually, okay, can be described into its own component. So means that in reality, this molecule move from this point to this point, and you could measure the velocity as q. Okay, however, this total velocity, the resultant of this velocity in mathematics can be described as the can be said that it has element of x direction velocity and y direction velocity. So for x direction velocity, it is written as small u. And for y direction velocity, it is written as small v, like this. Okay, so the existence of velocity component is actually can be proved in real life. So for example, if we have a river here, and a river here is flow at certain velocity, so means that this is the velocity of x component. So and then if you want to go from this point to this point, okay, what you should do is actually you need to maneuver, you need to run, you need to make sure that your boat is actually moving at this direction, because the additional this velocity, your boat's velocity at this direction will be interact with the velocity of x direction here, and then your boat is actually moving at this direction. So mean in this situation, we could say that you have two component velocity. One is the velocity of the river, act as x direction, and this will become another component of your velocity, means that the velocity of your boats, and then the resultant of the combination of these two velocities will result, mean the resultant velocity is your boats will flow straight like this one. So this is the basic idea of component velocity. So means that the component velocity is actually can be proved in real life. So here in physics, you must understand, you must believe that the existence of component velocity is actually reflect the real situation. So again, I would like to express here that the resultant velocity is shown as small q, and the velocity for x-axis is u, and the velocity of y-axis is v. And the relationship between the resultant velocity and the component velocity can be written like this one. So you have a q is equal to square root u square plus v square. So if you have three-dimensional, so what you need to do is you just add z's. I'm sorry, velocity for z is actually w. So you just add w square square root. Okay. Okay, so for the z-axis, the velocity is written as w. So and then to calculate the resultant velocity for three-dimensional axis, so you need to write q as square root of u square plus v square and plus w square. So this is, I think you already know about this. So and then I would like to introduce you about the polar coordinates. So the idea of polar coordinate is actually to reflect the motion, the circular motion. Because, for example, if we have a river here, and then the river flow at certain velocity, and your boat move at certain velocity, this motion is actually reflect in x and y axis like this one. However, in another application, for example, you have a sink here. A sink, you tap a water inside your sink, and then you release water flush into a hole. Okay, macam awak ada sinki, awak penuhkan air dalam sinki, awak basuh muka, basuh tangan dan sebagainya, dan awak alirkan air di dalam sinki keluar. Oleh itu, air akan bergerak masuk secara pusaran. So, when when a fluid move in circular motion, it is not suitable for us to measure or to locate the movement of the molecule by using the Cartesian coordinate. So the proper one is by showing them in polar coordinate. That's why you need to understand these two type of coordinate system. So you could read here the distance from the pole is called the radial coordinate or radius, and the angle is called the angular coordinate. So this is the two basic parameter that you should know in polar coordinate. Okay, so I will explain the explanation in previous slide. Okay, in polar coordinate, okay, so we take two basic element, which is the radius, because the radius here will show us the distance of particular molecule from its origin. So and then we will measure the angle here to show the location. So means that because if you have another molecule here or another molecule here, the distance from the center point here will be the same, because this is the radius of this circular shape. So to differentiate between this molecule and this molecule and this molecule, what we need to do is we define the angle from here. So this is the 0 degree. So you measure the angle here. So maybe here is 45, and you measure the angle here. So maybe this is 170 degree, for example. So and then you measure here. So maybe here is around 260 degree, for example. So the angle and also the distance of the radius will show us the exact location of certain particular molecule. So that is the way we show the polar coordinates. So we write as r and theta. So which is the r here is the length of the radius, and the theta here is the angle of this one. So the angle here can be in few units. For example, you may write as 45 degree, or you may write as pi over 2, or pi over 4, and so on and so forth. Or you may write in radian. Okay, so please be careful, means that you need to do your homework. So you need to study how to convert the 45 degree into pi, and how to convert pi into radian, and so on and so forth. So this is the common terms used in polar coordinate. So again, in polar coordinate also, we have velocity components. So the component is a velocity component which is parallel with the radius. And then another velocity is which is parallel with the angle here. So in certain textbook, it says that the angular velocity is actually the tangential velocity of this point, because you know that you have a circle here, circular line here. So and then you need to measure what is the velocity at this point. So it will become the tangent of this point. Okay. So and then to differentiate between Cartesian coordinate and polar coordinate, so we will use this term to show the component velocity. UR here is showing the velocity parallel with the radius, and the U theta here is showing a component velocity which is reflect the location of this angle, means parallel of the angle. Okay. So and then to calculate the resultant velocity, you may use this. This equation. So Q is the resultant velocity, is the square root of UR square plus U theta square. So if we have three-dimensional of this one, so we will have a Z axis. So the Z axis will show like this one. Okay. So for example, we have a circular here. So this is the value of radius. So this is the direction of theta, and this line will show us the value of Z, mean the Z axis. So the velocity of Z can be written as U and Z here. So it's just showing the velocity component of Z axis. So normally in this topic, we will discuss only two-dimensional motion, but I'm not so sure in tutorial we'll have three-dimensional problems or not. But normally, at least, please try to push yourself. Make sure that you could answer question for two-dimensional axis for this one. So and then that is the axis that you should know. We have Cartesian and we have polar coordinate. So we have a specific term to describe the velocity. So we have U and V for Cartesian coordinates, and we have UR and U theta for polar coordinates. So and then here I would like to introduce you one thing, which is the law of conservation for this system. So mean the law of conservation here is actually will reflect the continuity equation. as I said yesterday, that I hope you still remember the continuity equation that you use in fluid mechanics 1, which is A1 V1 equal A2 V2, or the mass flow rate, so which is rho 1 A1 V1 equal rho 2 A2 V2. So again, we will start our discussion from the continuity equation, because this is very basic, because you need to make sure that all your calculation must fulfill the idea of conservation of mass or continuity. Okay. In differential form, or normally when people discuss about the differential form method here, we will discuss about these three fundamental law. So which is, one is the conservation of mass, which is the continuity, and then the second one is the conservation of momentum, which is the Newton second law. So in fluid mechanics too, in conservation of momentum is actually reflect in Bernoulli equation, because it's telling you about the energy from point 1 to point 2. So and then we will have the energy. Okay, so but for this syllabus, we will not discuss thoroughly, we will not discuss detail about the conservation of energy, because normally in conservation of energy, it will involve the increment of temperature and so on and so forth. So but in fluid mechanics, we are focusing actually in flow of liquid actually, or flow of a gas that do not have any influence of temperature increment. Okay, so we go for the topic number 1, which is the conservation of mass. So we are now, we try to derive our own continuity equation. So I think you already discussed this one in fluid mechanics too. So I will go a little bit faster. So you may watch this video again and again, and you may snapshot this screen for your own notes. So in Porter textbook, they will use this diagram to show the equation, to start the calculation of equation of continuity. Okay, so this diagram actually, it's reflect, okay, so we could say it is actually the shape of one molecule. Okay, so maybe in a certain textbook, they will give us that molecule is actually in sphere shape, but to ease our calculation, so we assume that our smallest part in our fluid is a square like this, because we could easily say that the distance at this part is dz, because it is parallel, it is on a z-axis. So the distance from this one is dy, because this is a small part of y-axis, and the distance of here, okay, it is also equal to here is dx, which is a small part in y-axis. So and then we could write down, we could write down here. Okay, we start with the two-dimensional first. So if we write this diagram in two-dimensional, we could write like this one. So we have a square here. So and then we could say that the distance here is dy, and then we could say the distance here is equal to dx. So I think you already know why we could write this as dy, because it is a small part in y-axis, and this is a small part in x-axis. And then you already know in fluid mechanics 1, the basic idea of continuity equation. So it is about, if you have one system here, for example, we have a square here, so the input must be equal to the output. So means that for incompressible, so mean not for gas, you sometimes gas can be compressed. Okay, so the basic idea of mass flow rate is the input must be equal to output. Okay, so we start with the idea of mass flow rate. Okay, mass flow rate is written as m dot. So I think you already know this. So it is mass over time. So it can be write as m and dot. So this m dot symbol is a quite familiar symbol. So you know that m dot means that the rate of mass. So we call it as mass flow rate. And another equation to calculate the mass flow rate is rho, A, and V. So which is the rho here? Rho is the density. So I hope you could understand what is density. A is the cross-sectional area. Cross-sectional area, and the V here is the velocity. Okay. Another thing that you should know is the A here is a cross-sectional area which is perpendicular to the velocity. So means that if you have a pipe here, and for sure the velocity will flow like this one. So I hope you could understand this one. So because the average velocity will flow according to the shape of the pipe here. So, and then the cross-sectional area to calculate the flow rate here, which is Q is equal AV. A here must be perpendicular to the velocity. So means that if you have pipe shaped like this one, like a needle of your pichagari, for example, the flow, the velocity of flow is still like this one, because this is the average velocity speed, which is parallel to the shape of the hose. But the cross-sectional area here cannot be you cannot take this as the cross-sectional area. The cross-sectional area must be perpendicular to the velocity. So this is the very, very basic rules that you should know to calculate the continuity equation, to calculate the flow rate. Okay, so please be careful. Okay, maybe you have some different shape, nozzle and so on, the cross-sectional of nozzle and so on, but please make sure that you need to understand that the A there is the cross-sectional area which is perpendicular to the velocity. So and then okay, let's say we want to calculate the mass flow rate. So we go to this idea, rho, A, and V. So let's say we want to calculate the mass flow rate at this section. So the mass here is rho. Okay, the cross-sectional area here, A here, is actually the dy times the dz. So it's written here, dy dz, because dy is the height of this one, and dz is the width of this one. So the multiply of these will give us an area. So and then as we learned in previous slide, the velocity for x direction is u. So we could write the mass flow rate here is rho u dy dz. So and then for this section, for y-axis here, so we could write as rho v dx dz. So rho is the density, v is the component velocity for y-axis, and dx dz means dz here, dx, okay, dz is here, so dx is the length of this one, so means dx dz means the area of this one. Okay, so you have a velocity like this one, so and then you have an area here, so means you are calculating the mass flow rate. Okay, so how about this one? So this is also actually the calculation of mass flow rate, but we a symbol written here is showing that because we don't know, after a flow rate comes into a system, we don't know whether only velocity change or the velocity and also the density will change. Okay, di sini awak kena faham perkara ini kerana apa? Kerana kita cuba menyediakan satu equation yang sesuai untuk semua keadaan. We try to prepare equation that suit with all condition. So all condition means suit with compressible condition and incompressible fluid. So for incompressible fluid, so for sure the density is constant. So means that the changes will not, the density will not change. However, if we use gas as our medium, so gas has possibility to be compressed or to expand itself. So when it compress or it expand, so the density will change. So then sometimes the changes is not only occur on the velocity, it also could occur for the density. Okay, that's why we write the terms at the outlet here is like this. Okay, yang ini adalah step paling penting awak kena faham. So kita seolah perlu membuat penilaian berdasarkan kesemua keadaan. Maksudnya kita kena pastikan bahawa equation yang kita buat memenuhi keadaan compressible, maknanya aliran yang boleh dimanfaatkan, ataupun incompressible, aliran yang tidak boleh dimanfaatkan. Okay, yang paling mudah kita akan ambil aliran yang boleh dimanfaatkan. Membawa maksud selepas sesuatu sistem, sesuatu fluid di sini pada inlet masuk ke dalam satu sistem, okay, kemungkinan ia akan keluar di dalam 3 keadaan. Pertama, mungkin velocity sahaja akan berubah berbanding dengan velocity inlet. Kedua, mungkin velocity tidak berubah tetapi density akan berubah, ketumpatan. Itu condition yang kedua. Condition yang ketiga, kemungkinan kedua-duanya berubah. Maksudnya velocity akan berubah sedikit dan dalam masa yang sama density pun akan berubah sedikit. Oleh itu, ketiga-tiga keadaan ini kita mesti express, kita mesti nyatakan di dalam equation. Oleh itu, kita tulis sebagai ini. Okay, saya padam dan kita lihat. Okey, jadi rumus ini sebenarnya masih lagi berpegang kepada idea rho AV seperti ini. Okey, cuma kita gunakan dy dx sebagai pemalar. Dy dx, dy dz di sini akan reflect dy dan juga dz. Dia akan reflect kepada cross sectional area. So ia membawa maksud bahawa area untuk inlet dan area untuk outlet tidak akan berubah. Okay. Dan terms di belakang ini menunjukkan perubahan yang berlaku di dalam density dan juga velocity. Itu sebab kita menulis di dalam terms ini sebagai rho u campurkan dengan del partial differential untuk rho dan u del x pada paksi x dan dx. Okay, so jadi membawa maksud partial del u di sini, saya rasa awak belajar di dalam tajuk matematik engineering dan juga di dalam differential dan juga integral sebelum ini. Partial membawa maksud kemungkinan perubahan itu berlaku di kedua-dua bahagian. Kerana kalau kita ada del over del x untuk rho dan u, okay, saya tulis mula. Okay, sekiranya kita ada del over del x untuk rho u, so kita boleh menulis sebagai del rho over del x dan kita fixkan nilai u, kita campurkan dengan del u over del x dan kita fixkan nilai rho. Okay, boleh nampak So di sini membawa maksud, okay, kemungkinan akan ada keadaan di mana berlaku perubahan sedikit pada density dan berlaku juga perubahan sedikit pada velocity. Okay. So sekiranya equation ini perlu digunakan untuk incompressible flow, maksudnya keadaan di mana density constant. So if the condition is incompressible flow, which is the density is constant, so we could write as because there are no del rho over del x. So it only have du, dx, and rho. So we could write this term into rho u plus del u del x dx and dy dz. Okay, that's why in certain textbook, okay, in certain textbook, I will show you here later on. In certain textbook, they write here as, they write this term as, so the basic idea is rho a and v, and we know that the density is not changes, and the area here is not changing. So the only possibility is the changes of velocity, whether the flow is become slower or faster. So they write as rho a in bracket u plus du. So means that at outlet, it may have possibility to have u and an extra u. So the du here means the changes that occur for the velocity. It may be positive or it might be negative. If the changes is negative, so means the value of u at outlet is less compared to the velocity at the inlet. Okay, so here I think you already know why we write rho v plus d del rho v over del y dy dx dz. So dx dz is the cross-sectional area, and this term is showing the changes that occur maybe for density and also the velocity. Okay, so I hope you could understand this one. So and then we go to the basic idea to evaluate the total mass flow rate that enter that element. So the ideas that you should understand is this one. M dot in minus m dot out is equal to del dt m element. So m dot mean mass flow rate. So mass flow rate inlet minus with the mass flow rate outlet must be equal to d dt. So del dt here means the changes of time. Mass element, mass change with time at the system, at here. Okay, so we evaluate this basic condition first. So let's say we have system of incompressible flow like this one. So we have a system here, and this system is incompressible. So incompressible means the density will not change. So if the density is not changed, okay, we could say that, okay, we assume that in this system, all the fluid will fill this system, this tank, for example. So the inlet here must be equal to the outlet, because there are no space for this molecule to stay in this tank. So means the basic idea is, if you have 1 liter inlet here, so because this tank is full with water, so for sure you need to pull out another 1 liter here. So maknanya kalau awak ada satu tangki penuh dengan air, kalau awak masukkan 1 liter air, sudah tentu 1 liter air akan perlu awak keluarkan supaya flow berlaku. Jika awak tak keluarkan 1 liter, so 1 liter pada inlet di sini tidak boleh awak masukkan, kerana sistem telah penuh dan sistem pun tidak boleh dimampatkan. Okay. So dalam keadaan ini kita mengatakan bahawa del dt m elemen di sini akan sama dengan kosong. Kenapa sama dengan kosong? Awak kena faham bahawa maksud del dt m kita boleh tulis juga sebagai del m over del t, bermaksud changes of mass with time. Maksudnya perubahan mass yang berlaku di dalam perjalanan masa. So oleh kerana tangki ini telah penuh, oleh itu kita kata tidak akan ada berlaku pertambahan mass mengikut masa. Maksudnya pada minit yang pertama katakan 5 kg, minit yang kedua pun 5 kilogram, minit yang ketiga juga 5 kilogram. Oleh itu, dm dt di sini akan sama dengan kosong. Oleh itu, kita boleh tulis sebagai m dot in equal to m dot out. So, inilah yang kita belajar di dalam fluid mechanics 1. So, kita akan mengambil idea bahawa mass flow rate at inlet must be equal to mass flow rate at outlet. So, this is the very basic idea. And we transfer it, we try to expand this idea into differential form. Okay, let's say we have an incompressible system. So, incompressible system, it can be something like this. So, we have a tank here, and this tank still have certain area, certain volume to be fulfilled. So, mean if you give 1 liter here, maybe 0.5 liter will remain in this empty volume, and the outlet here is 0.5. So let's say we have 1 kilogram here, and then we have 0.5 remain in the tank, and 0.5 is flow out. So means that here we cannot say that mass flow rate inlet is equal to mass flow rate at outlet, because in reality 1 kilogram here is not equal to 0.5, because we know that another 0.5 is remain in the system. So we need to we learn about the basic idea of the conservation of mass. So mean 1 kilogram here is actually equal to 0.5 that remain in the system, and 0.5 plus 0.5 that flow out from the system. So we could write as mass flow rate m dot in is equal to mass flow rate out, this one, plus with dm dt. So dm dt here means the changes of mass in this system over time. So means that at minute 1, so the mass is maybe here, the blue mass is maybe 10 kilogram, and after a certain time, so the mass is changing into 10 kilogram plus another 0.5 kilogram. So the changes of mass over time is written as dm dt. So from this idea, we could rearrange the idea becomes m dot in minus m dot out is equal to dm dt. So so I hope you could understand this idea. So, and then let's say we have a compressible flow like this. So the compressible flow is when we have gas in the system. So we know that, for example, a cooking gas in our home, so the gas compressed into a tank and it's become liquid, and then when you push the valve, so the liquid of the gas will evaporate into a gas. A liquid will evaporate and turn into gas. So means the gas is compressed into liquid, and then at certain situation, it can turn itself into gas. So for compressible flow, okay, so same idea. Maybe we could input the gas here. So the gas will become a liquid at this tank, and then maybe the flow out here is not as equal or not the same with the inlet. So we could write as m flow rate at inlet is not equal to mass flow rate at outlet. So we could again say that why it's not equal here, because there are changes in system inside this tank. So the changes can be written as del m over del t plus mass flow rate at outlet here, So, and then again, we could write as mass flow rate at inlet minus mass flow rate at outlet is equal to del M over del T. So this is the basic idea that you should know. If you read the textbooks, so they will give you that this is the basic equation that you should know to derive or to start to derive your continuity equation based on our basic axis. Okay, now we try to derive our continuity equation based on this diagram. So first, you need to understand this term. So mass flow rate inlet is minus mass flow rate at outlet is equal to del M dt, mean the changes of mass inside that element. So and then the mass flow rate is equal to rho A and V. So which is rho is the density, A is the cross-sectional area, and V is the velocity. So in this term, okay, we could write that, we could assume that this is the inlet and this is also the inlet. And this is the outlet for the x-axis and this is the outlet for the y-axis. So we could write as rho u dy dz inlet and dv dx dz is the inlet minus, because the equation here is minus, so we have minus here, minus with the mass flow rate outlet for x and mass flow rate outlet for y, and then it is equal to del dt. So we write del dt and we need to write the mass of the element. So mass of the element here can be written as this one. So how to calculate the mass? Okay, mass, we know that previously in our study, density is equal to mass over volume. So this is the volume. So and then to calculate mass, we could say it is equal to rho times volume. So rho is rho here. I hope you could see the equation. So we have rho here. So and volume is dx, dy, and dz. So previously I show you the cube diagram like this one. So the x here, the z is here, and the y is here. So the multiple of these three length will give us volume. So the mass here is equal to rho and volume. So we multiply the value of rho with dx, dy, and dz. So and then I hope you could do this in at home because it quite simple. Okay, so the basic idea is, so we have you have rho u here multiple with dy dz. So this minus here could cancel this value. So and then you could solve everything. So you could say that by simplifying the terms, you could get this one. Okay. So and then to how to get the zero here is by taking this term to the left hand side. So and then this is only for two-dimensional. So if we want to add the three-dimensional, so we put the z direction here. So we could just copy the flow here. So we add with del rho w over dz plus d rho dt. So d rho dt is actually value that comes from the right hand side here. So and then from here we could write like this one. So how to turn this into this term is by expanding the value of this one. So as I said previously, if del rho v over del y, it can be written as del rho over del y and fix the value of velocity plus del v over del y and fix the value of rho. So by using this idea, okay, you need to expand all this term and then you could rearrange this term into this one. That's why you have del rho over del t. So it is here. And then you have u del rho dx, v del rho del y, plus w del rho del z plus rho. Because if you expand this, you will find that the constant of rho here will can be separated. So we have rho du dx, dv dy, and dw dz is equal to 0. So this is the very common differential continuity equation from a 4 Cartesian coordinate. So I hope you could try this at home. Please make sure that you could write the diagram, you could label it, where is the inlet, where is the outlet, you could write that's du dy very well, and then you could do these steps again and again, okay, to make sure that you could comes out the final product of continuity for Cartesian coordinate as this one. Okay. So and then for the case of incompressible, a flow in which density of a fluid particle does not change as it travels along, the continuity equation could written as this one. So what is this meaning? Means that if we are solving incompressible fluid, means the density is constant, so mean the value of rho here. So you must know that the density is constant is not equal to density is equal to 0. Please be careful about this term. Okay, density is constant membawa maksud ketumpatan adalah tidak berubah. Ketumpatan itu ada nilainya, tetapi nilai ketumpatan tidak berubah pada inlet dan juga pada outlet. So membawa maksud nilai rho di sini tetap wujud. Awak jangan simply kata, oh incompressible, density is constant, then density is 0. So awak cancelkan semua nilai rho sama dengan kosong, so awak dapat kosong. Itu bukan cara yang betul. Awak kena faham bahawa density constant membawa maksud tidak ada perubahan density. Density tetap ada. Contohnya air, density air adalah 1000 kg per meter padu, dan air kita boleh anggap ia adalah incompressible fluid. Dia adalah cecair ataupun fluid, benda yang tidak boleh kita mampatkan. Oleh itu, density air di mana-mana jua di mana-mana di dalam titik sistem, ia tetap sama. Pada inlet, di dalam sistem, pada outlet, so density air adalah sama. Oleh itu, apa yang awak boleh kosongkan ialah nilai ini. Del rho del z, del rho del y, del rho del x, dan del rho del t. Membawa maksud, del rho del t kenapa boleh sama dengan kosong? Kerana kita anggap bahawa tidak ada perubahan density terhadap masa. Maksudnya, pada minit pertama, density dia 1000 kilogram per meter padu. Pada minit kedua pun tetap sama, 1000 kg per meter padu. Pada minit ke-10, pada minit ke-100 dan sebagainya, density tetap sama. Oleh itu, del rho del t sama dengan kosong. So, sama juga del rho del x, del rho del y, del rho del z. So, del rho del z ni membawa maksud apa? Maksudnya, perubahan density pada paksi x. Kita kata tidak ada perubahan. Okay, so yang ni saya harap awak dapat faham. Ada kalanya matematik itu awak perlu faham berdasarkan perubahan ataupun kepada physical evidence yang berlaku di dalam sesuatu sistem. Okey, bukan sekadar mengatakan oh del rho del z, kenapa nak density bahagi dengan jarak z? Okey, so dia tidak membawa maksud nilai density itu dibahagi dengan jarak z, dia membawa maksud kecerunan sebenarnya. Maksudnya perubahan yang berlaku terhadap density di sepanjang paksi Z, di sepanjang paksi Y, dan di sepanjang paksi X. Okay, yang itu yang awak kena faham. Oleh itu, nilai ini semua akan sama dengan kosong. Okay, dan nilai rho di sini juga kita kata secara mudah kita boleh pindahkan ke sebelah kanan dan dia akan menjadi nilai kosong. Okay, sebenarnya secara matematik mungkin awak lebih mudah faham. Kita kata dan rho bawa ke sebelah kanan sama dengan kosong. Sebenarnya bukan itu yang secara fizikalnya berlaku. Fizikalnya berlaku ialah oleh kerana incompressible, this term will become zero. Then we have rho del u del x, del v del y plus del w del z is equal to 0. So in these mathematical terms, we have two possibility. One is the rho is equal to 0, then the value will equal to 0 here, or the value in bracket is equal to 0, mean the du dx plus dv dy plus dw dz is equal to 0. So yang ini saya harap awak faham. A darab B sama dengan kosong. So kita ada yang sebenar ada 3 kemungkinan. A sama dengan kosong, B ada nilai, atau A ada nilai, B sama dengan kosong, atau memang A dengan B adalah kosong, so kita akan dapat jawapan kosong. Okay, sama juga dalam keadaan ini, kita mengatakan bahawa rho kemungkinan kosong, atau nilai dalam bracket sama dengan kosong, atau dua-dua kosong. Tetapi fizik selalunya akan reflect logic. So kita katakan bahawa density tidak akan kosong. Kerana even gas yang ringan pun, kita ada udara, nitrogen, oksigen dan sebagainya, masih lagi mempunyai nilai density. Oleh itu density tidak akan kosong. Density kosong membawa maksud tidak ada sebarang elemen. So density tidak akan kosong membawa maksud hanya nilai di dalam bracket sahaja yang akan kosong. Oleh itu kita boleh tulis sebagai ini sebagai continuity equation untuk Cartesian coordinate bagi keadaan incompressible flow. Untuk keadaan compressible flow, memadai awak menulis seperti nilai ini. So ini adalah continuity equation untuk semua keadaan, compressible dan juga incompressible. Tetapi jika kita hanya menilai incompressible flow, memadai untuk awak menulis nilai ini. Kemudian sekiranya kita discuss hanya dua dimensi, 2D coordinates, so kita anggap bahawa dw dz, kerana apa dw dz boleh equal to 0? Kerana kita beranggapan bahawa tidak ada komponen velocity of w. Maksudnya tidak ada partikel yang bergerak ke arah z. Oleh itu kita anggap bahawa nilai ini akan sama dengan kosong. Oleh itu memadai untuk kita mengatakan bahawa continuity equation for two-dimensional axis and for incompressible fluid can be written as this term. So saya harap untuk kali ini awak dapat melukis gambar rajah dengan elok. Okay, you could label all the diagram, you could create your own square diagram. So, and then you could derive your own continuity equation, and finally you could derive the simple continuity equation for incompressible flow like this one.